Good afternoon, everyone, and welcome to these PSYCHE guest lectures. On our program today, we have two lectures, but before we start, we would like to stress some practical points. Please all turn off your cell phones and put your microphone on mute. If you have communications or questions, you can use the Q&A function in the Teams event. Our first speaker today is Lilia Ben Mustafa from CERTECH. She graduated from the Catholic University of Louvain at the Faculty of Bioscience Engineering with a master's degree in chemistry and bioindustries and a specific orientation in nanobiotechnologies, materials and catalysis. She is working at CERTECH since 2 years in the Chemistry and Industrial Process Department. She is active in the field of process intensification, namely developing safer, more productive and less energy-consuming processes, such as the conversion of industrial processes from batch to continuous production. She will give a lecture on syngas purification to meet Fischer-Tropsch specifications, which is related to our project. Our second speaker today is Professor Kevin van Heem from Ghent University, who is also the coordinator of the PSYCHE project. Professor van Heem is specialized in thermochemical reaction engineering in general and in particular the transition from fossil to renewable resources, including the thermochemical recycling of plastic waste. He will give a lecture on process intensification and innovation by multi-scale analysis and design. So we will first start with the lecture of Lilia.
During the presentation, I will first introduce the PSYCHE project. Then I will talk about the part we are working on at CERTECH. I'll start by talking about plastics. So we use plastic products to help make our lives cleaner, easier, safer, and more enjoyable. From plastics in the clothes we wear, the houses we live in, and the cars we travel in. So plastics are extremely versatile materials and are ideal for a wide range of consumer and industrial applications. And plastics have also again showed their usefulness during this coronavirus crisis. However, a major part of plastics ends in our environment or disposed of in landfills. So plastic pollution is a topic that has been gained traction in recent years, and it is already seen as a global challenge. So just to have an idea, in 2018, 359 million tons of plastic have been produced worldwide, and 8,300 million tons since the 50s. From this total amount, 70% have become waste, of which 84% have been disposed of in landfills or in the environment. Given this situation and to tackle this problem of plastic waste accumulation, different measures have been taken. The reduction of plastic for single-use applications and the diversion from landfill and incineration to mechanical recycling has been set up. And for those plastics that are too degraded or too contaminated to be reprocessed through mechanical recycling and reintroduced in the production cycle, there is chemical recycling solution. So during chemical recycling, post-consumer plastic waste is converted into valuable chemicals to be used as a feedstock by the chemical industry. So you can see that the new plastics economy is a circular economy where plastic wastes are valorized. So, as I said, chemical recycling could be used as complementary solution to mechanical recycling, where the latter proves to be unsuited to materially recover plastic because it is too degraded, contaminated, or too complex. So, in contrast with mechanical recycling, chemical recycling is an industry in its infancy, and most plants in the market are in pilot stage. So as you can understand, chemical recycling of plastic waste is still under development, and different European projects have been or will be set up in this field. The PSYCHE project is one of them. It is a project funded via the Interreg program. This project is a collaboration between Ghent University, Université Louvain, L'École Nationale Supérieure de Chimie de Lille, CNRS, and CERTECH. So let me talk a little bit about CERTECH. It is an R&D partner and supplier of analytical and technological services in the field of chemistry. Our mission is to provide innovative solutions for the improvement or development of products and processes. We have different expertise in the field of materials, chemistry and industrial processes, and also environment. In the field of plastic economy, we have teams of experts working on the development of bio-based polymers and on the mechanical recycling of plastic wastes by extrusion. We also have an expertise in chemical recycling by pyrolysis to convert plastic wastes into fuels. So in this field, we already worked with different industrial partners, and it is a growing area. We also have an extended activity in the field of air quality, including the detection of different toxic molecules and the development of different abatement ways. We also contribute to the transition to what we call the factory of the future, by assisting industries in developing more effective and less energy consuming processes of production. So as you can see, we have different activities with interconnected expertise to tackle environmental, societal, and economical challenges, and that always in agreement with the principle of sustainable chemistry and circular economy. So now let's go back to the PSYCHE project. To be a little more precise, the project is about the conversion of plastic waste to base chemicals by what we call Fischer-Tropsch synthesis. So now I will take every step of the process and explain it briefly so you can understand the general idea of the project. We start by gasification. So plastic waste stream will enter a gasification reactor, and during this process, the raw material is heated in presence of limited oxygen. There are several types of gasification in which especially the temperature can vary. In this case, for plastic to monomer applications, gasification is generally done at 900 and between 900 and 1650 degrees. At the end of gasification step, we have what we call syngas, composed of steam, carbon dioxide, methane, carbon monoxide, and hydrogen. Carbon monoxide and hydrogen will react later during the Fischer-Tropsch process to produce monomers. Gasification output also contains impurities, mainly acids, ammonia, organic molecules, and some dust and particles. So before Fischer-Tropsch process, the syngas has to be purified from these contaminants and processed to increase its quality. So syngas processing consists in firstly converting methane to carbon monoxide and hydrogen through what we call steam reforming. Hydrogen over carbon monoxide ratio is then improved by water gas shift. And finally, hydrogen is purified from carbon dioxide. The most used techniques for this last step are pressure swing adsorption, consisting on the capture of carbon dioxide over columns containing activated charcoal, or by using scrubbing, where the carbon dioxide is absorbed in a solvent. Generally, we use amines. These two techniques of purification are also used to get rid of some contaminants, and we will see them back later. Then hydrogen and carbon monoxide will go through Fischer-Tropsch process. It is a catalytic process that will lead to the production of liquid hydrocarbons. The process is generally done at temperatures of about 150 degrees to 300 degrees. And it is done in presence of metal catalysts, generally iron, cobalt, ruthenium, or nickel are used. But as I told earlier, there are contaminants also exiting the gasification process. The gas entering Fischer-Tropsch process has to be purified from these contaminants, mainly to preserve the catalyst from poisoning and inactivation. But this purification is also important so these contaminants do not finish in the atmosphere. So syngas purification is what we are working on at CERTECH, and this is what I'm gonna talk about during the rest of the presentation. To summarize, plastic waste go through gasification. At the end of gasification, we have syngas and contaminants. The product of gasification has to be then purified from contaminants, and before entering Fischer-Tropsch process, the syngas is processed. And at the end of the whole process, we have liquid hydrocarbons. So as I told, we at CERTECH work on syngas purification. The main team working on this part of the project is composed of two of my colleagues, Mathieu Dubois and Dominique Lalande, and myself. Mathieu Dubois is specialized in chemical recycling and has 5 years of expertise in raw material valorization by pyrolysis. Concerning Dominique Lalande, He is specialized in the field of air quality and abatement techniques. I would also like to mention François Collignon, Benoît Cartezer, and Laurent Bilteris for their helpful advice throughout the project. To start, here is a list of the different contaminants exiting the gasification reactor. This list has been established in collaboration with Ghent. As you can see, acidic and basic contaminants are expected. Also some particles like silica and ashes, and a variety of organic compounds. As you can see, the first type of contaminant that we have to deal with is particles and ashes, as ashes and silica particles together represent more than 2% of the effluent. So we will see the different existing technologies to capture particles. We will also see the different selected techniques to purify syngas from the different gaseous contaminants. I would like to highlight the fact that there is a wide variety of techniques to capture gaseous contaminants. But we have to keep in mind that at the end of the process, we want to recover hydrogen and carbon monoxide for Fischer-Tropsch synthesis. Consequently, in this case, some techniques are not adapted. I will take an example. So, for example, for organic compounds, oxidation processes are used in industry. The process of oxidation is performed at high temperature in a combustion chamber in presence of oxygen. It leads to the production of water and carbon dioxide molecules, and it is an exothermic reaction. In the case of syngas purification, this kind of process cannot be used because of the potential oxidation of hydrogen and carbon monoxide. With this example, you can understand that it is important to select techniques that will keep untouched hydrogen and carbon monoxide. One of the techniques to get rid efficiently of organic compounds and other contaminants is condensation. So by decreasing the temperature, some contaminants will condense to a liquid. Of course, the temperature to reach depends on pollutant nature and the desired residual concentration. So this cooling step is also interesting to stop the potential secondary reactions in the effluent exiting gasification. Generally, condensation is performed in tubular heat exchangers, where the hot fluid will move in a counterflow arrangement compared to the cooling fluid. So the cooling sources that can be used may be water or air, with operating temperatures of about 10 to 20 degrees. Or we can also use cryogenic fluids like nitrogen for lower temperatures. A heat transfer will allow to cool the gaseous effluent and condense some of the contaminants. This technique can be used to capture tar molecules, as the boiling points are generally between 100 and 300 degrees. And this technique, to some extent, can also be efficient in acids and ammonia capture by water condensation. So condensed water may capture acids and ammonia by absorption. By using this system, the energy transferred to the cooling fluid may be reused further in the process, for example, to heat back the syngas before entering the Fischer-Tropsch process. So now let's deal with the particles treatment techniques. As I mentioned before, one problem with the effluent exiting gasification is the presence of dust and particles. Indeed, particles may deteriorate some equipment by abrasion or reduce the performance of the next processes downstream. There are different available techniques to capture these particles. There are cyclone filters, venturi washers, pocket filters, and electrofilters. Let's start with cyclone filters. In cyclone filters, the raw gas is subjected to rotary movement. Under centrifugal force, particles agglomerate against the walls of the filter and then fall under gravity. For a more efficient capture, multi-cyclone packages consisting of several small cyclones can be used. Cyclone filters are simple and reliable devices, but present a lot of clogging risk, and this technology is not suitable for fine dust. So cyclone filters may be used as a pre-treatment for particle capture. Then there are venturi washers composed of three elements: a converging section, a throat, and a divergent section. Water and gaseous effluents are injected in the converging section, where the mixture is accelerated and the liquid is then sprayed. Droplet formation increases contact surface between water and gaseous mixture, and particles are captured in these liquid droplets. This technique is also suitable for hydrochloric acid capture, but is not recommended for effluents heavily loaded with particles because there are risks of clogging. It is important also to know that venturi washers have an important consumption of water and need downstream processing. In electrofilters, particles passes between two electrodes. One of them will ionize the particles and the other will collect them. In contact with the collecting electrode, ionized particles will discharge before falling under gravity at the bottom of the filter. This installation is suitable for fine particles and does not involve maintenance costs. But this treatment technique may be, in this case, dangerous in presence of hydrogen. And finally, there are also pocket filters composed of rows of filter bags. The gas that we want to purify passes through filter bags, and particles are trapped, forming a filter cake at the surface of the filtering medium. This technique is used to collect particles of about 0.1 to 1 micrometer, and provides good performance for installations of small and medium particles, medium capacity. Choosing pocket filters involves some maintenance costs, because during use some pocket bags may perforate by wear and tear, and drilled pockets leads to to a lower performance of purification. Gas temperature is an important parameter, knowing that filter bags may be deteriorated at high temperature. And the most used filtering media are limited to 150 degrees. So the condensation process before particles capture may be really interesting in this case. Okay, now let's deal with acidic contaminants. As we have seen, the exiting effluent from gasification also contain acids like hydrogen chloride and potential presence of sulfur dioxide. To neutralize these acids, calcium hydroxide is generally used as an alkaline reagent. Through this process, the gas is injected in the reactor containing lime particles. At the exit of the reactor, pocket filters will capture lime particles that may be transported by the fluid, and salts produced during neutralization. For hydrogen chloride treatment, sodium bicarbonate is also useful, and for sulfur dioxide, you can also use sodium bicarbonate or limestone, but in presence, this process is done in presence of oxygen, and in this case, it's better to not use processes including oxygen addition to avoid syngas oxidation. In addition to condensation and acids neutralization, absorption can be used to capture the residual gaseous pollutants by transfer from gas to liquid phase. There is a physical absorption based on the affinity of the contaminants for the solvent, and there is also chemical absorption consisting on a diffusional mechanism followed by the reaction of the contaminant with solvent molecules. To increase the efficiency of the process, it is possible to act on diffusional parameters. Temperature is an important parameter, and low temperature leads to better diffusion. Another important parameter is the contact surface between gas and liquid. So increasing this contact surface, for example, by spraying the solvent, allow better exchanges. And finally, the contact time has to be sufficient to allow the diffusion in the solvent. So the contact time condition is the size of the washing tower. There are different types of washing towers. We have a column with trimming. In this type of washing tower, gas and liquid are circulating in countercurrent. The liquid flow through a porous lining and a porous lining and form a liquid film in the pores, creating a higher contact surface. In the column with the sprinklers, gas and liquid are also circulating in countercurrent, and the liquid is sprayed increasing contact surface between solvent droplets and gas. The third type of washing tower is tray column. This type of column also works in countercurrent. In the column, you have perforated trays that allow the gas to flow. The liquid flowing under gravity creates liquid layers through which gas passes. Water is generally used as scrubbing liquid for acids like hydrogen chloride or hydrogen cyanide. For sulfur dioxide, adding a basic reagent like lime or sodium hydroxide improves absorption processes. Water is also efficient for ammonia absorption. So to improve ammonia absorption, adding sulfuric acid is also possible. Concerning hydrogen sulfide capture, this contaminant can be removed by using aqueous solution of amines. In this case, it is a chemical absorption. Generally, monoethanolamine is used, but secondary and tertiary amines can also be used. It has been reported that methyl diethanolamine show good absorption capacities for this contaminant. Otherwise, ethylene glycol derivatives may also be used for physical absorption of hydrogen sulfide capture, but the absorption is less efficient than with amines. Concerning organic compounds, we can use organic solvents like saturated hydrocarbons or biodiesels to capture these organic contaminants. So it's a way to capture the residual organic molecules that have not been captured by condensation. And as a final capture technique, to eliminate the residual contaminants, adsorption technique can be used. It consists on capturing pollutants by adhesion on the surface of a porous solid. The efficiency of this process is increased by lowering the temperature as adsorption is exothermic. Adsorbate concentration is also an important parameter, as by increasing pollutant concentration, the adsorbate will be more rapidly saturated. This is why this technique is used as a final way to capture pollutants. The most used adsorbent is activated carbon. This adsorbent is efficient in capturing different contaminants. The principal function of this type of adsorbent is the capture of organic compounds, including dioxides. Activated carbon is also efficient in absorbing residual acids. Two techniques are used to put pollutants in contact with the adsorbent. The adsorption can be done in a fluidized bed or in a fixed bed. In fluidized bed, adsorbed particles are suspended in a column by the gas flow, and in fixed bed, adsorbent particles are packed in a column. The fixed bed has better capture capacity due to a longer residence time compared to a fluidized bed, but present high pressure drops. When the adsorbent is saturated, the column is then regenerated. Generally, it's done by increasing the temperature or by depressurizing. So here you have an ideal configuration of the installation for syngas purification. At the exit of gasification, we can start by removing a significant part of organic compounds, and to a lesser extent, maybe some other contaminants like acids and ammonia by water condensation. This technique allows to reuse the heat to warm up the syngas at the end of purification process. After condensation, we have to get rid of particles present in the effluent exiting gasification. And different types of particle filters can be used in a row to have an efficient particle capture. Then we have acids neutralization, and finally, to complete contaminants captures, absorption and adsorption techniques may be added to the process. Adding absorption and adsorption processes depends on the efficiency of the upstream processes. So as you could see, there are different types of contaminants and different ways of abatement. All these technologies have their operating conditions, and for each step you must take into account different parameters like the temperature of the effluent, the flow rate or concentration of each contaminant. So setting up this type of installation is a real challenge, and purification step is the major contributor to the costs, capex and opex costs, and it contributes to the cost of producing the syngas. But it is an important part of the whole process, and we cannot do without it. So thank you for your attention, and if you have any question, I will do my best to answer. Otherwise, my colleagues Mathieu and Dominique, who are way more experienced than me in this field, are present. And here you can also find my contact information if you have any more questions.
This is a word from our sponsor. So I will speak a bit about process intensification and innovation by multi-scale analysis and design. So I will start with also a short introduction about the Laboratory for Chemical Technology. Laboratory for Chemical Technology has a very long history, but you see the main concept that was applied in the group on this slide. And what you see is that what we try to cover is across this red line, and we really want to go from fundamental understanding of the chemistry to the process, and therefore you need well, in the central element you need the kinetics. The kinetics effects can help you to design a proper reactor, although that's not strictly needed, but I will try to illustrate that this has some advantages if you know the kinetics in quite some detail. And we apply these things to all kind of processes, being catalytic and non-catalytic. and gas phase, liquids, and solid materials. And I will try to illustrate for 2 of those systems how we work and what the advantages of applying this approach. And these were some pictures that illustrate also a bit more what we do. And on your really right side, you see the detailed chemistry that we try to implement either on the catalyst, but even in polymerization processes. And if you saw that the combination of tetraeders, then it's a bit, well, nowadays we have a bit of a different approach. So we try to take a lot more advantage of the computational power that is available. We do that by performing ab initio calculations for the kinetics, so really take a lot more advantage of that. But we apply computational fluid dynamics a lot more than what we did in the past, and thanks to the increased computational power, obviously we can also account better for the chemistry. And this means that well, one thing drives the other. However, for me, still the most important thing is the experimental part. And I think that's one of the strengths of the group is the fact that we can also test this, the things that we design, for example, based on computational fluid dynamics. So experimental data is for me always crucial and are the most convincing. What we try to cover with LCT is a lot more than in the days that we were called LPT. So the name used to be LPT before 2010, Laboratory for Petrochemical Technology. Now we do a lot more. We have people really working in polymer design, like my colleague Dagmar Dove. We have people working in catalyst design, like Vladimir Alvita and also Mark Sijs. Circular process design, so we do a lot of work in on plastics recycling, but also looking at other waste streams. We have low carbon technologies. This means that processes that don't produce a lot of CO2, or where we try to do something with CO2, and that's also related to the efforts that we undertake to look at renewable chemicals. Also, I will give an example of this in this presentation. And finally, we have our, I would say, hardcore expertise is really the reactor or reaction engineering that allows us to scale up to the process, and that's really still a big strength, where I think all the people that you see on the right make different contributions to. What I also would like to say is that as a group you can only do so many things, and I realize we do a lot, but we all are chemical engineers. And this means that, well, if you really want to go for drastic innovation, I believe you also need different skills. And that's why a few years ago we have established in Ghent what we call the Center for Sustainable Chemistry. It's like a super group which covers about 40 faculty, and they work among others on green chemistry, on bio-based chemicals. You have the capture plot platform, which is under that umbrella, and so those people are intensively collaborating on different applications, and I think this is really has driven research in our university to, I think, to a new level, and we were able to make connections that well, never in the past were never done. This is also a fact. So all the people that working in chemistry or chemical engineering and so on, then well, they are not always greeted with a smile. the perception of the chemical industry is even worse than banks that get us in terrible situations. And typically, if you see people then in the news, then they show a cooling tower where steam is sent in the air. So it's a combination of, I would say, ignorance and probably an easy target that really puts us in the news, and typically not always with good things. Typically, chemistry comes only in the news when things are bad. And I think we have to fight against that perception, but I think among others, we also have to try to maybe educate the people a bit better and explain them why these things are happening and why it is important that there's actually things being constructed and that it also contributes to their welfare. Because if you look at the chemical industry in Belgium, then there's no country in the world where the chemical industry has this kind of impact. If you look at what the GDP, and this is now from 2009, but if you would do the same thing in today, then there's no other country where the chemical industry has this kind of impact on the GDP. So yeah, there are two ways to deal with the system. Of course, we can say, well, everything can be produced somewhere else, not in Europe, or can be in China, for example. Or we can understand and make everything as good as we can, and basically force other people or other countries to produce things at the same, for example, CO2 cost as what we do. And I think that last thing is definitely the right path forward. And then you have to understand how the chemical industry works. And that's always also quite difficult. Well, the chemical industry is a bit like a tree where you have the roots, and these are the raw materials. And we have about 10 of those, and the oil is one of them. Natural gas is another one, biomass and others are there. You can also call waste as part of that raw materials. And those are transformed typically to fuels or liquid energy carriers, and they are the basis for base chemicals. And if you look at base chemicals, then you have examples like olefins. These are ethylene, propylene, 1,3-butadiene. And then we have also aromatics. We have syngas there, synthesis gas, what is being studied in PSYCHE. And we have ammonia and others. And then we go to other intermediates, acetic acid and so on, and then to consumer products. So this is how the chemical industry is built up, and this will not change rapidly because this structure is in place and is associated with enormous investments. So making a huge change in short periods, I don't believe that it will happen. And you see how these products in the end are converted one after the other, and then you see that well, many of these intermediates then are being produced by a single process, and that's starting typically from C2, C3 or naphtha feedstocks, and that's called steam cracking. So this is the main process to produce ethylene, but also benzene, and even components like butadiene and so on. So that all comes from one single process, and that's the basis of the whole chemical industry, how it is built up today. This is also what is the case in Belgium, and the Flemish government is aware that the chemical industry is crucial for welfare of this country, but also the steel industry is very important. But these industries are responsible for substantial CO2 emissions, and they recognize this, and this is of course a threat for the industry. So that's why they have established what they call moonshot projects, where the objective is that by 2050 the industry would be the chemical and but also the steel industry would be almost CO2 neutral. And that's of course a very big challenge, because if you look at which kind of process that we have, then well, we have steel production, which is one of the biggest emitters. Here in Ghent we have ArcelorMittal, which is responsible for at least 4 to 6 million tons of CO2 directly, also something indirectly. But also we have petrochemical centers in Antwerp with refineries and steam crackers, which are also responsible for substantial amounts of CO2 emissions. And this drives what we are working on in LCT. So of course we try to gain energy efficiency improvements. We look a lot at electrification, so the concept of applying green electricity. Hydrogen can be an important intermediate, and if you look at electrolysis today, that's economically still quite difficult, but if compared to steam methane reforming, so something needs to be done there as well. And you see many other things that we are working on. Among others is the waste streams, which is the concept of the PSYCHE project. Why this focus on green electricity? Well, it's a fact that today there's not enough green electricity to support everything what we like to do, and even not to drive our cars and so on. But many people believe that in the near future it is possible to have substantial larger amounts of this renewable energy being available, and this really can change how we operate chemical processes, but also steel production, and it could drastically help to reduce CO2 emissions. And I will give a few examples how this could work. For example, you see it here. Here we have a steel plant where you could reuse part of the CO2 that's being produced by the process, and by, for example, a plasma-driven process that uses methane and converts it together with the CO2 back to CO. So there's like recycling. But then you use, for example, plasma, a thermal plasma, to create the energy to convert that. The biggest emitter of this next to the steel industry is olefin production, and that's olefin production is the main end product of the PSYCHE project, and the reason is because mostly, well, waste gases are used to heat up the reactors. So all these processes are executed in very big furnaces. And there you basically have combustion of a gas consisting mostly of methane, but also some hydrogen that's being converted and ending up in CO2. And for example, for like the steam cracking process, 90% of the CO2 emissions come from the furnaces. So if you can electrify the furnaces, then you can already reduce 90% of your emissions, considering that all your electricity would come from green electricity. And this is even made clearer here. So this is a situation for the Flemish industry. And you see here, so the chemistry part is the blue part, but the main part is there actually the steam cracking furnaces. So it really could reduce with almost an enormous amount, about 5 to 10 million tons of CO2 if we go to electrification. The same holds also for steel, and that's a bit of the concept of the Moonshot project. If you look at olefins, then and if you look at olefins in the PSYCHE project, then of course you have to compare it to the state of the art. And if you look at what is on the table today, then, well, these are all things that are actually being carried out at different TRL levels. I think the lowest TRL is the OCM process that you see really in the middle. But you see here that so all the CO2 emissions related to energy, and you see that, for example, for naphtha and ethane steam cracking, so the SC stands for steam cracking, then contributions are the lowest, lower than for Fischer-Tropsch steam cracking. What you also clearly see is that using coal is stupid. I cannot call it any other way, but making olefins from coal, that should be forbidden. It's actually being done in China for substantial amounts, but okay, I think that if you look at the emissions, I think you can really doubt if this actually makes sense. And you have both energy related, but also chemical CO2, which is the result of gasification of that coal. So we in the end have to develop a process which is better than the current state of the art. And one of the elements is the starting material, which is not shown on the slide, but the starting material is if it's fossil or something that is a waste, is also an important contributor in overall CO2 emissions. So this is the concept that we want to go to, is going to a more sustainable world, a more circular model. There are different ways to end up back with the original plastics that we started from, but I think gasification is definitely one of the technologies that's on the table. It has definitely advantages that it could basically work with the whole plastic waste material. So it does not always require that you sort things. It can also work with what they call the residues, the bottom of the barrels in oil terms, but and in this way create back the monomers, and from those monomers you create back the polymers that we started from. Of course, you have to understand that with every step, so that you do, every process step, is it Fischer-Tropsch, is it gasification, there's a substantial capex investment. So going to fewer steps is definitely of interest from a capex point of view, and also from an efficiency point of view, because in every step you typically lose something. But this is what we do in PSYCHE, is that we have really plastic waste. We pre-treat it, we gasify it with in a vortex reactor technology that you also will be seeing coming back in this presentation, and then we end up with syngas that you just saw how it can be purified, and then we go to Fischer-Tropsch. And here you see it from right to left, so with the plastic gasification, the syngas purification, the Fischer-Tropsch synthesis, and then we want to go back to the olefins. So I hope it's more or less clear why we want to go to olefins. But of course, we have to compare to the state of the art. And if you look at LCT again, then we have a very long history in olefin production, going back to the 70s. So we know quite a lot about this process, and we are still working quite intensively on it. What I will show you is that the concept of how we apply process intensification, how we do it. I will start with a simple demonstration case. And then we'll move back to a more advanced demonstration on a solid material. And here you see all kind of definitions of process intensification. You can find different books and different terminology. I like terminology of Professor Stankovic, and but in the end it's quite simple. It's doing more with less, and this can be smaller volumes, can be less energy, can be creating more products. So there are many different things that fall under process intensification, also in the field of separation and so on. Why do we want to do this? Well, it's clear that if you look at our world, that everybody in the end wants to live more or less how we live, and so everyone wants to have the same welfare. So there will be probably an increase in emissions. There will be an increase in demand, not necessarily in Europe, and we don't have enough resources to, in the end, to do all these things. if we can make processes more efficient, technology better, then we lose less, and hopefully we can close the whole system. If you look at the basis of process intensification, the basis is the multi-scale and the different scales that you can see of the processes. And with process intensification, you want to improve at a certain scale the process in this kind of way that everything becomes a lot better. You can do this by developing new catalysts. It can be by being clever in materials. It can be by better design, but it can be on any of these scales. In the end, hopefully ending with a unit that is substantially smaller than, for example, the unit that you see here on the right, which are steam cracking furnaces. And smaller means than cheaper. And so in LCT, well, this means that we, in the end, combine all these different elements. So we combine the detailed chemistry, the kinetics, the CFD, experimental, and then we use that for the process. But we create certain optimization schemes in there to make sure that in the end we end up with what we call the most optimal technology. Good. So this is again the slide, and you see how CFD can help. It can give you very nice colors for directors, or cleverly forged data. I've seen those as well. So you don't really always have to believe what you see, but if you apply it properly, then you really can gain a lot of insight, and it really can avoid you to build many different units. It can help you to make wise choices, I would say. And what CFD is, in short, is that we have fluid flow, and we have a set of conservation equations. So it's species and global mass. We have an enthalpy balance. We have a control volume, so where we have the continuity equations, and we have, of course, momentum balances that we account for, and we solve that by a clever solver. And in this way, we can get a solution that hopefully is reliable. Obviously, the solution is dependent on all the boundary conditions that you apply and all the assumptions that you make. So typically, if your solution is converged, okay, you get a solution that's based on all your boundary conditions. Yeah, your boundary conditions will, if you impose wrong boundary conditions, of course, your solution is not wrong, but you get a result, but that does not necessarily mean something. That happens more than you think. The reason that we use more of these computational fluid dynamics simulations is that the computational power has drastically increased, and we have made a movie. You can find it on our website, where we show you how supercomputing really helped us to develop new designs and to avoid making stupid mistakes. In the end, what we still do is nothing more than what we did maybe 20, 30 years ago, but the conservation laws that we account for, so we solve them in 3D. Typically, they will always had one-dimensional reactor model equations, and this always means certain assumptions. And these are valid to a certain respect by allowing to account for 3D. Then you really see also more in boundary layers what actually is happening, and you see that if you look at heat transfer, but also certain site reactions, that actually those things are crucial to improve the process. And I think that has made a substantial difference if you compare it to what we have been doing in the past 20, 30 years ago. That really helped us to go for innovation. So this is the view from almost my office, and you see many experimental facilities, and they play a crucial role. So computational fluid dynamics are nice, but you need experimental data to support and to convince somebody that what you have done computationally actually also makes sense and can be proven. And so you will see that approach coming back in the coming slides. The main challenge there is analytics. That's what a lot of people forget if they look at reactive systems, is you have to be able to measure what comes out of your reactor. And you have to do that in such a way that you can close your balances. This does not only mean mass balances, it also means molar balances. And that's why we have invested in our group enormous amount of time to really close balances. So in this case, we have an outlet section of a unit, and what we do is we inject an internal standard, in this case nitrogen, and based on the amount of nitrogen that we inject after the reactor, we can basically back calculate the complete composition of the effluent gas. And you see here we have nitrogen. Based on nitrogen, we can calculate methane, and the methane is then used on different channels of our GCs in this way to calculate absolute values of components. And what you hope, of course, is that when you add up all these amounts of all these components, that you end up with 100%, and that also your mass and molar balance is close. Is this true? The fact that they closed 100%, I think this never happened. 100.00%, I think this never happened. But it can be very close. And then you recognize that you really have good data. So, but the crucial element that you need is that, well, you need a complex analytical system containing, for example, multiple GCs or GC times GCs, and you will see why we try to use GC times GCs in our work as much as possible. If you really look at exotic systems or like gasification even, then you have contaminations, for example, sulfur or nitrogen. Then what we do is we inject internal standards, specifically for those components. And we have selected detectors like the detectors that you see here, what we call a sulfur chemiluminescence detector. And that the detector only sees sulfur components in this case. We have the same thing for nitrogen, it's nitrogen chemiluminescence detector. And these are basically detection limits of ppms. They don't have overlap with other components, so you really get a very pure signal of these components, and it means that you can also detect trace components. And this way you can also close the molar balances of these smaller compounds, like sulfur and nitrogen. And that's in the end what you have to do. In all of these processes, is it now pyrolysis or gasification, you will end up with a liquid or a tar fraction. And that's also more complex than what you think it typically is. And here you see how such a GC times GC looks inside. And what you do with the tar, for example, is that you inject it. You inject it on your first column. Then you have a modulator. You send it to a second column. And that second column is in this case connected to an FID. It can be to the time of flight MS for identification. But in this way, we create two separate separations that can work together and get improved resolution. So here you see examples of that, of a kerosene in this case, or it can also be a tar fraction. But you see that the components with from 9 to 10 carbon atoms are properly separated, but they're also separated by class. So they're not only separated by carbon number, they're also separated by structure. So naphthenes, dinaphthenes, monoaromatics, dinaphromatics, and so on. And this is confirmed by the time of flight MS that you see in the bottom. And this means that you can do a very accurate quantification. The good thing is that always this component, so in this case it's dodecan, is eluting always at the same spot. So yeah, it's very difficult to be wrong. So from an accuracy point of view, this also helps, and it avoids that you misassign components because your components are well separated and they always are eluting at the same spots. This is now a bit more advanced. So if you inject a complete gas, then you see a light part, and you will see that's properly separated based on a one-dimensional chromatogram. But you see a lot of tar components, so polyaromatic components. And with this GC times GC, you really can go to 4 or 5 aromatic rings. You see those here, and even those you can detect and measure and quantify because you work with an internal standard being either methane or something else that you inject. You even see the unconverted and paraffinic feed, which is not overlapping with anything else, so you can really also quantify conversions also very well. And this is the amount of resolution that you get, and most people will find this too much, but this is something that we like because we really like to model things in full of detail, and you really see all the different polyaromatic components that we are forming with different side branches and so on and so on. So really get an enormous amount of information. You can apply this in principle to any system, but I will give an example on the production of green olefins, where we have worked on together with Neste, among others. So here is what we have looked at, and on the right you see a system from petroleum with Tyson Foods. This is chicken fat that you start from. You hydrotreat it, you get what we call HDO fat. You can also do hydrocracking. You get these kind of liquids again, and you see the amount that you get is determined with GC times GC. You see the same thing. You can do the same thing from pine wood, where you have a very interesting fraction, what we call tall oil, and also that oil is quite interesting and is quite complex. So you can crack that and produce, in this case, olefins. And you see that you get a really nice spectrum of compounds, and you get enormous amount of details of different components that you are forming. Also, small amount of CO2 with this system, and you can actually close the mass balance and molar balances of this complex system. So now that I've tried to convince you that we can get accurate data, then getting data is something. We use that data to validate our chemistry. So many different groups in the world, they have developed what they call network generators. So kinetic model generators, can also call it that way. And you see here an example of all these groups that are working in this area. And I think we collaborate with most of them, but maybe most intensively with the green group at MIT. And also we have developed our kinetic model builder. And you see that one here. This is the Genesis model builder. I will try to explain you why we believe that that's one of the better model generator and what the value is of that kinetic model generator. The starting basis of that kinetic model generator is a chemoinformatics system. So it's how you represent a model, a molecule. And in this case, we have chosen not to use something in-house, but we have used one of the best open source packages to start from, which is coming from the pharmaceutical world. And based on that representation, you can basically represent any molecule that is present in a period, almost from the periodic system. So any atom from the periodic system, and that's the starting point. You see how it works here. So we have, for example, these kind of molecules, and what we do with Genesis is that we can represent them in a certain automated way that the computer can understand. And then we, of course, have to tell the computer when reactions occur. So we have to explain to the computer, okay, if these bonds are present, then these reactions can occur. And sometimes you cannot allow certain reactions. So you also have to explain to the computer, sometimes don't do this reaction. And this is a bit how we do that. So first, of course, we have the molecular representation. So we have a structural formula. We can go to a 3D structure. From that 3D structure, we can find a graph structure. And using that graph structure, we can get, for example, SMILES or INCI representation. And we use these different representations in the end to then perform what we call permutations, which are the reactions. The good thing about all these representations is that they also allow you to define groups. And what we also have in our group is what we call group additive models. And these group additive models are used to calculate thermodynamics, for example. So here you see the previous molecules. It's separated in different groups. And for each of these groups, we have a value, and you add up all these values. And in the end, you have the thermodynamic of that species. That's based on Benson thermodynamic databases. The principle of group additivity, of course, works for thermodynamics. But of course, you also have sometimes some non-nearest neighbor interactions, and so we also have to account for those and contributions of symmetry. And Genesis can also account for that now quite accurately, but that's quite challenging. We use that system also to define kinetics, because of course, if you have a kinetic model, you don't only need species reactions, but you also have to tell how fast this reaction is actually occurring. And you have to make sure that the estimate that's being used is pretty close and that it's easily to assign. So also for that aspect, we have developed different methods that we have implemented in Genesis, and that allow the program to come up with reaction rate coefficients in an automated way, but using a certain database. This is the end result. So we apply Genesis, we generate the kinetic model, we don't change anything to that kinetic model, and then we test it, for example, in this case, pyrolysis process, which is methyl decanoate pyrolysis, and a different component, which is methyl 4-decanoate. We have generated the kinetic model, we simulated our experiments, the experiments are the dots, and you see we get a very good agreement for the dominant species, but also for the minor species. So this means that we are now confident enough that we can generate for a whole variety of systems, for example, carbon, hydrogen, oxygen, but also now for sulfur and nitrogen, quite some detailed chemistry without having to do a lot of things manually. And this is, of course, from a time point of view, a serious time saver. Typically, to do something by hand for one of these molecules, it will take even an advanced model generator almost 1 year to generate a decent model. So if you can do it automatically, then you could probably reduce that with factor 10 to 100. Good. Another critical aspect in what we do is that we don't work with simple feedstocks. Also in the PSYCHE project, we work with complex feeds. And what you have seen previously, and in the previous example, these were all model components. And this is how many people reason, is that they go for a model system and then they assume that everything that was done for the model system also works for the real feed. We have learned that typically is quite risky, because if you look, for example, at plastic waste, there are quite some contaminants, but also in refinery process, you have quite some components that are maybe small in amount, but have huge influence in the end of the end result. And so therefore, a critical aspect is what we call feedstock reconstruction. So is how do we go from global properties of the feedstock to the detailed composition? And the first time that we did this was in my PhD, which is now almost 2 decades ago, is where we developed such a program, and we have in the end now commercialized this to come up with feedstock reconstruction. In simple words, how does it work? So you have global properties that you see here. It can be, for example, average molecular weight, paraffin, isoprene, naphthene, aromatic component composition, elemental composition, specific density, any combination of what you have, and you press on the bottom, and then the feedstock composition comes out. So this avoids the characterization step. This sounds like magic, but of course, with some good mathematics, you can get there and we will try to illustrate a bit how that works. One of the methods that we have implemented is what we call the maximum Shannon entropy method. And what this in the end does is it creates the statistically most probable composition that meets all your boundary criteria. For example, if the boundary condition would only be a molecular weight, it will create a composition that has that average molecular weight, and it will get you some kind of distribution. If you provide also density, then that composition will change, and it will make sure that also the density is matching with the one that you have provided. And so in this way, you can build up the complexity and provide more and more properties if you have them available. So this is what we have called this module. So we have called it SIMCO, simulated composition. And you see how we start from the bulk properties that you see on top. And then we have two options. We have this maximum Shannon entropy method that I just explained to you. And then we also have neural networks. We have different people in our group that are working on neural networks or deep learning methods. And those work on huge databases of feedstock composition. And based on the bulk properties that you provide, that neural network is trained and generates the detailed composition. Obviously, this will be, well, always more accurate than the Shannon entropy if this is in your database. Yeah. So if you have a feed that is in that fitting database, then of course this will always be the right path. But in most cases, then you have something that is just outside your database, and then we have to resort to a different method. Good. So these are the results that we get. And you see here the comparison between the experimental, which is the black line, and then the simulated line that we get with our compositional model. So this is pretty good. So now that we also have this part covered, so this means that we can really close this whole system, is that we can really go from global feedstock to products if we model the reactor properly. We have generated now the kinetic model, and now it all depends on how we model this reactor. It can be 1D, 2D, and 3D. In the following example, I will give you an example of steam cracking. I will have to explain you that it's, well, not that simple. Yeah. For many of the processes that we look at, being gasification or combustion or pyrolysis, we have free radical chemistry occurring, and this means that we have millions of reactions occurring. And this means if you would account for all of them, you would have a kinetic model with millions of reactions, and this system would never solve, even in 1D. So not even speaking in 3D, so this could never work. So that's why what we have done in Ghent is that we have drastically simplified this whole system. And this means that we have accounted for chemical intuition, so chemical understanding of pyrolysis or gasification. And this means that we can, instead of accounting for these millions of reactions, we only have to account for 14,000. That's a substantial improvement, but still quite difficult. But if you look at really for the species that for which we have to solve, we end up with a system of about less than 1,000 molecules that we have to solve. Even that is today too much for computational fluid dynamics, but we have been able to solve systems with hundreds of molecules by accounting for the chemistry. So really adapt our solvers to account that they can take into account the details of the chemistry. But this is in the end a crucial part, is going from millions of reactions without losing accuracy to something that is that actually can solve. The kinetics are almost entirely ab initio based, so we really do a lot of ab initio calculations, mostly using Gaussian for the gas phase chemistry, and we account for tunneling with Eckert tunneling corrections and so on. And these are all things that are accounted for in our chemistry. They're implemented in Genesis, and in this way we end up with, for example, the values that you see on this side. So what we have done is that we have for this reaction, we have calculated the activation energy based on reference value and then contribution that are calculated based on group additivity, because this reaction is slightly different than the reference reaction that you see here. So we have to correct that activation energy with the differences that you see on this slide. All these things are done automatically. And then we validate this whole system. We do that with steam cracking pilot plant data. And this is the result that we get. So these are now the kinetics that are validated with group additivity. And you see that if we implement those, that without tuning anything, we can get a good agreement with our simulation, with our experimental data. So I hope that I can convince you that also the modeling thing is working properly, even if we scale it up to an industrial scale. So these are now industrial data of a real industrial plant without any tuning, and there's a decent agreement for the main product. So I've tried to illustrate now that we can really go from fundamental to really to process with our concept. Obviously, we have a lot more data than what I showed you previously. We have a lot of data for a whole range of feedstocks, and we use that data to improve our models and not only work with the ab initio data, but really to tune our models. And in the end, we valorize our models and we sell those models to companies. Good. But of course, this doesn't mean any process intensification. And this is the talk of the subject of this talk. So then I have to explain you something else, is that if we went to this last process, then a lot of things are happening. So we have the product that you get, but you also get things like a side reaction that's occurring, and that's what people call coke formation. So during olefin production, you get in a tubular reactor, you get a carbon deposition on this reactor, this tubular reactor, and this means that over time you get really buildup of cokes and you get an insulator. So this means less and less heat would be going to the process if you would not increase the heat input. Of course, you can increase the heat input, that's one way, but you can also be more clever. So you can come up with different designs of the reactor that really allow you to create better heat transfer. This can be fins or rifle tubes or any strange shapes, and all these things have been considered or are being considered in the past. So if you now have the steam cracking process, then you see that, well, our big enemy is this carbon layer. And you see that in the end, it builds up completely and it fills up the tube completely. So you only have the small passage where you can have the gas going through. You can solve this by having better heat transfer by creating more surface. But if you increase the surface, this means that you always get a pressure drop, an increased pressure drop. And now you have to know that the increased pressure drop is negative for the selectivity of your products being the light olefins. And this is really what we want to avoid. So we really want to come up with better designs that allow you to get higher yields, but at the same time have a very low pressure drop. Okay, so this is what has been done in the past. So this is the currently best technologies which are available. These are profile tubes. You see here, some of them have very strange shapes like the scope design. And what they in the end do, they create better mixing. And I think it's intuitively clear that if you try to simulate this thing in 1D, this will not be useful. So we really have to go to 3D to account for all these 3D obstacles to get somewhere. And this is what we have done. This is part of a European project that we are coordinating, which is running at its end and which will end in November. And improving the selectivity and reducing coke formation are one of the critical things that we need to do there. But it's a very complicated thing, and it's like the good, the bad, and the ugly. So the good thing is that well, with these 3D reactor technologies, we can increase heat transfer. And if you increase heat transfer, we believe that we can reduce the temperature at the wall. And if we reduce the temperature at the wall, we get less cokes. If you have increased that heat transfer, then we created probably an extra obstacle. So this will result in an increased pressure drop, and we get lower selectivities. The question is that really there? So that's already quite difficult. So that's the bad part. And then we have the ugly part is if we create these kind of technologies, how will they perform over longer times? So we are not interested to work over 1 year. These technologies have to survive 5-10 years. And one of the things that's happening is carbonization, for example. So will our tube that we have developed survive all the wear that we create? Okay, so we have looked at this system in the past decades almost. So the first thing what we have done is that, okay, we were able to simulate these reactors in 3D. That was the first step in detailed chemistry. And that showed us that okay, we believed that the current designs were not that optimal. These were the fin tubes. But what we saw is that our computational approach that we used on computational fluid dynamics, we used run simulations, so Reynolds average simulations. So we showed ourselves that was not always that accurate, and we had to go to large eddy simulations with detailed chemistry. And large eddy simulations, this means that you account for turbulence in a more accurate way, but this is also computationally a lot more challenging. And that's why we had to develop something that allowed us to do that also in a reasonable time, even if we had access to these HPC. So we had developed a speed-up system that basically allowed to look at our system like what you see on this animation, is that we were able to track a piece or a plug over time, but doing that in 3D. So once we had that, then and we could do that in full accuracy, then we were convinced that, okay, now we can use this thing and we can go to innovations. And you can try to do innovation on your own, but we found a very good partner in the Van Karman Institute that provided us with very good validation data. And they created, for example, these two setups, so a setup with particle image velocimetry and something with liquid crystal thermography. And what you see here is basically a tube going from right to left with some obstacles that you see here. And these obstacles, you see, they result in zones with improved and reduced heat transfer. And with this optical axis, we could actually measure those, and we could use those for validation. The same thing we could do with PIV. So for non-reactive systems, we could use that data set for validation and to convince that our models were really accurate. And here you see, for example, some of the examples that we looked at. So these are the run simulations that you see here with the dotted lines. You see here the LS simulations with the full lines, and then you see the experimental data provided by the Van Karman Institute that agree quite well with the LES simulations. So we are able now to simulate the reactor in 3D, albeit non-reactive, but also grab all these secondary effects in full detail with our LES simulations. And then, of course, we took this to the next thing, and then you see some of the results that you see here on the right is, well, trying to improve the design. And we took this in our sequels. We did it for a few dollars more. So we improved that tubular design, and we got inspired by golf. And Clint Eastwood was running out of movies, so but we know he liked golf, so that connected to our whole story. And we cloned basically a golf ball with a tube. So we ended up with not this thing, but a tube with dimples on. And we did LES simulations that you see here, and we got these very interesting results that we got, well, that the flow coming out of this dimple actually was shifting. It was going up and down. And this is what people call a self-cleaning effect. and you really see this periodic behavior, and this helps to keep the tubes clean, and is sometimes even used to avoid icing. And this good effect is one beneficial effect, but these dimples also create improved heat transfer with minimal cost of friction. And this means that in the end we patented this tube design because the dimple design outperformed every existing technology. And you see, for example, here that we got improved product yields with reduced pressure drop compared to other technologies, and low wall temperatures, which are associated to low coke formation. Good. It looks like this. So it's a Gulf meets a steam cracking coil. And you see how indeed process intensification is being done. So in this case, we have to provide less heat to the process. We get more products, more yields, higher yields, and we get less coke formation. So this was really the good thing about the system. But we have further optimized this. And we have not only looked at dimple design, we have in the end optimized the shape, and we ended up with a new kind of geometry that we're currently testing, and that's basically the heart shape. So that's also being patented, and that is, according to us, almost the end of our story about steam cracking. So we are now convinced that we have like almost the best design, but all driven by computational fluid dynamics and experimental testing. So really intensifying the process. For us, you can say it stops here, but that's not really true, because in the end, it's nice to do this even on pilot plant phase. We are now taking this to industrial phase, and we are doing this not alone, but we are doing this with several partners. You see some of the demonstrations that are currently being done in Dow. This is now for other designs, but also for the dimple design. We hope to see that demonstrated really soon at industrial facilities. And this is then the ultimate proof that in the end, what you have done computationally, how you intensified really the process, that also really worked. And in this way, we have drastically already improved the CO2 emissions of the steam cracking furnaces, reducing that with approximately 30% by a combination of solutions in this improved project. So we made already a substantial step, but this is still not CO2 neutral. So we still have several steps to make it really CO2 neutral. I will end with a different illustration, and that's going to the vortex reactor design. The vortex reactor design is what you see here. So what you have is that we have a flow coming in tangentially in something in a structure that has certain veins, and this gas flow is distributed over this ring and is then entering and is basically leaving through the center. And you can see that that center is in this case here. If you see my pointer, then you have the gas coming in this case on top, and it leaves through the center after some rotation. Typically you have solids in there. It can be catalyst, it can be a solid material, it can be plastics, it can be many different things. It can be sand, and then you leave with the gas there. What you see is that in these systems you have the drag force, and you have your centrifugal force. So your drag force is compensated by your centrifugal force, which is a lot better than in classical fluidized beds, where you don't have the centrifugal force, but where you only have gravitational forces. And in this case, the centrifugal force is a lot higher than the gravitational force. So you can have a lot higher slip velocities and really have process intensification in this kind of reactor technology. And that's basically the magic about the gas solid vortex reactor. It's not a reactor in this case that's rotating. You really make the particles rotate, and this rotation means that you really get intensification of the process. To make that even clearer, you can see it on this slide. So we have this fluidized bed reactor where we have the drag force and the gravitational force. We have this vortex reactor. We have the gas flow, and here we have our centrifugal force and that centrifugal force is substantially larger than the gravitational force that we have here. So this means that the slip velocities can also be higher. This can also mean that we have higher gas velocities, and higher gas velocities means that we can have very short gas residence times. And short gas residence times is beneficial for a lot of processes, among others, gasification, but also pyrolysis and, for example, oxidative coupling of methane. Over the last 5 to 10 years, we have been working on this with the whole team in Ghent, among others, colleagues Guy Marin and colleagues Geraldine Heinrich, Mark Zeiss. And we have made different steps to convince ourselves that this reactor technology can be useful. And you see here examples of biomass being rotating non-reactively, and you see really that we get a very nice stable bed with biomass, and that we want that we can keep the biomass in there if we want that. This is now the latest version of our reactor design. So this is the gas is coming in tangentially. It's starting to rotate. We have here the slots. In this case, we have 8 inlet slots, and then in this case, the biomass is rotating, and we are really looking on top or from the bottom at the biomass which is being rotated. So you see here a bit closer the gas inlet slots. You see here biomass that's rotating. You have what happens when you start reacting with biomass is that, well, you will have char formation if you do, for example, pyrolysis or gasification. Then you see here the small gas, more char particles. They cannot stay in this bed, so they are naturally removed with the gas. And so when things become too small, they leave really to the central exhaust. So it's also a natural separation of that small particles, being char in this case. So in that way, the gas solid vortex reactor is also quite beneficial for many processes, because it also allows you to separate unwanted products like char in a very good way. And here you see an example of a demonstration that we did with fast pyrolysis of biomass. So in this case, we have nitrogen that we have used as driving gas. We have biomass that we have used as inlet flow, and we have tried to regulate the bed at a stable temperature. So you see here the gas inlet temperature, but you see here really the bed temperature, which was very stable, and this is over the complete bed. So there's almost no temperature non-uniformities. And this is, of course, very beneficial for any process if you have perfect control over the temperature and almost a uniform temperature, so within 3 degrees over that period. So we had a very stable operation, and we did that now with Pinewood, and we have compared our results with classical fluidized bed reactors. And here you see results of 4 fluidized bed reactors, and you see here the amount of liquid yields. Because if you look at biomass fast pyrolysis, then your objective is to create as much as possible from this red bar, so this bio oil, and very little gas, and preferably not too much char as well. And what you see is that if you compare that, even if we put error bars on this picture, then we have 5 to 10% higher bio oil yields in the system. So that's really is enormous, and this is attributed to the perfect temperature control, but also the fact that we can avoid a lot of secondary reactions because of the very short contact times and very fast quenching that we can realize. Even if we take a closer look with our system, so we have a GC times GC also on that unit, and if we do make a detailed analysis and we look at all those products, this helps us to understand actually what is happening. So you see that the bio-oils are very complex, and that characterization is not easy. It's very tedious. You see here the quantified fraction in this case from the carbon fraction is only 23.5 weight%, but believe me, this is enormous. You also have an enormous water fraction, which is 15% typically. But based on the analysis of all these components, you can also understand why this vortex reactor is actually good. And you see that an important element there is what we call guaiacol kind of components. These are primary products which are formed from biomass, and they are like an indication of the quality of your reactor, because the more primary products that you have, it means that well, you really have avoided the secondary reaction, because otherwise these components will go away in many of these other reactors. Here you see the ratio of what we call catechol, which are then the secondary type of products. So we have catechols and phenols. These are secondary products coming from these guaiacols and this unit. And you see that in an Auger reactor, really this ratio is high. That's unwanted. So we really have a lot of secondary reactions, long residence times. In a fluidized bed reactor, it's already better. But you see in the gas solid vortex reactor, we have a lot more guaiacols in that system, and that shows you that we can really drastically avoid secondary reactions in that system. We use our CFD understanding because we can also simulate the gas solid vortex reactor in this way. So you see some of the results there, and we have compared our gas solid vortex reactor in this paper with fluidized bed reactors, and also there we saw that we got substantially larger biomass bio-oil yields compared to classical fluidized bed reactors, and that we can play with conditions, maximizing the bio-oil yields depending on gas flow rates and temperatures. So in this way, this avoids us that we do a lot of experiments, but it avoids us also that we do endless designs, because of course we cannot build many units. For example, we have the possibility to change the number of slot rings from 8 to 10 to 15 to and so on. So with the CFD, we can optimize the number of the number of vanes in our slot ring, and that's also what we have done. So we have currently designed also with 16 vanes that we are testing, and we have tested, and we are going to test even more. But you can also make this what I call nice colors for directors movies. You see here particles flowing, and then you can also get time averaged data. You can also see very nice flow lines. This shows you what the gas is actually doing, and this proves also the point that the behavior in this reactor from the gas point of view is that well, it's not that far away from plug flow behavior. So we really have the gas entering and then leaving through the central exhaust, and that is quite good. You see here the gas, the streamlines of solids or liquids, they really stay inside the reactor. If we want that, we can also make sure that they leave if at a certain point. But with the computational fluid dynamics, we can really show that we can optimize that design and also even look at other processes. And another process that we have looked at is oxidative coupling of methane. You saw that in one of the beginning slides. That's a promising process also to produce olefins. It's a single-step process instead of going to syngas. It really goes from methane in a single step to olefins if you have a good catalyst and if you have a very good reactor. The catalyst is not so much the issue anymore. We have thousands of catalysts which have been tested, but the reactor design is quite challenging. And also for this, the vortex reactor, I think, is one of the 3 best candidates that is suitable for OCM. And if you look at OCM, then you see here really the residence time distribution that you get when you have a tracer passing through the system. And in a perfect plug flow behavior, you see that we would only have a very sharp peak. This is not the case, but again, if you look at it, it's quite close to plug flow behavior, and we have very short residence times. And this is really milliseconds, and that's also the order of magnitude that you need for OCM. So in this case, we have millisecond residence times of the gas phase in our reactor, and that's desired in this our reactor. And these are results of Laurien van der Wallen, who just obtained her PhD 2 days ago. She also looked at a different kind of combinations with catalysts, and then looking at the most optimal combination to get the maximum selectivities, and also to try to operate the reactor autothermally on this ignited bench. So we even have looked at this in a combination with CFD, and that's also part of our PhD, so that we can also, from an energy point of view, drive this process in this vortex reactor really to the optimal conditions, and also from minimal energy consumption. So really ignite the bed and then operate the unit on the ignited bench. And here you see the ethylene mass fractions. So they're all very high. The C2 selectivities can be extremely high in this reactor. And this is what we are currently testing experimentally. We have obtained our first results this year, but due to COVID, we are lagging a bit behind, and we have not been able to confirm all the results from our simulations yet. There are many publications on this. This is just a list on the gas solid vortex reactor. So this presentation will be shared, so you have plenty of time to look at different things. What I have tried to illustrate you during the past hour is that if you combine all these fundamental aspects, so detailed quantum chemistry, accurate thermochemical data, automatic reaction network generation, clever reduction of that kinetic model, and then integrating that in 3D reactor models, accounting properly for also turbulence, then you can really go far. This is not easy, and we do this with codes that are in-house, but most of them are based on open source. So we work mostly with OpenFlow, and using those codes, I think we are quite confident that the results that we get are not so much calls for directors, but they really are guiding us and helping us to patent new technologies. And in the end, we can even demonstrate that the patented technologies actually work, as demonstrated with steam cracking, but also with biomass phosphorysis. We can actually prove it with experimental data that we can intensify the process and get very nice data and new reactor designs. So this is what I believe is the right way to go. Design should be, of course, guided by experiments, but theory is then a combination of computational fluid dynamics with detailed chemistry, and in this way, I want to end, and I thank all these sponsors for providing the funding for this project. Okay, I'm willing to answer any of your questions. So I will see what happens in the chat.
This brings us to the end of the PSYCHE guest lectures. To end, I would like to thank both the speakers for their interesting presentations and all of you for participating and attending to these guest lectures. I would like to acknowledge the funding received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the provinces of West and East-Flanders, the Walloon Region, and the Walloon Public Service on Economy, Work and Research.